Greetings, physicists. In this lecture, we're going to discuss significant figures, scientific notation, and units of measurement. Basically, how to measure something and how to record data. We will start with measurements. So I'm just going to draw here. Whoops, I can draw. Let's pretend I have good drawing skills. That is a plank of wood, if you can't tell from my amazing drawing. And we're going to measure how long it is. I'm going to measure it using my ruler. Now my ruler has two markings on it. It starts at 0 meters and it goes all the way up to 1 meter. So it's just a meter stick. So I'm going to try and measure how long this piece of wood is that I've got above. Well, I got a pretty crummy meter stick here. It's really only got 2 markings on it, or 0 markings on it, if you want to be picky. I mean, I put that one there, but if this was a true meter-long piece of wood, it would be, 0 to 1 meters like this. So we kind of have to guess. Every measurement has a guess in it. Well, here's how you're going to guess. I like to eyeball things, so I'm going to divide my ruler up and say that this is probably about the halfway point on the ruler. And it looks like that piece of wood goes further than the halfway point. And if I divide up this way and go halfway between the midpoint and the end, visually speaking, I can see that the piece of wood does not go that far. Now, we'll say that if I'm going to guess, that piece of wood is probably about 0.6 meters long, and I would record that. Now, you don't have to agree with me. I mean, it's definitely between 0.5 and 0.75, right? If this line I drew here is about a half. Now, of course, that depends on how well my eye can divide things up. I may not have gotten that half point quite right, but I'll bet it's at least there, or that the piece of wood is at least past halfway. And if we say that this is 0.75 because that's 3/4, yeah, we can be pretty sure that it's between those two numbers. But you could guess something else. You could guess that it was actually further along. It's 0.7 meters. That's a thing. So if you disagree with me, as long as your answer falls between those two lines, you're probably okay. All right. Now let's do another thing here. Let's erase a few things. Let's suppose I use a better meter stick. Let's suppose I use closer to a real meter stick here. Get rid of all my little markings there. Redraw my lines. Not a real meter stick, but let's say I use a meter stick that's got 10 markings on it. So let's go 1, that's 5, 4, 3, 2, 1. I'm hand drawing these, so they're not going to be perfect. 6, 7, 8, 9. And the end of the meter stick will be 1 meter. So now we've really got some, and then I'll mark that as 0.5 just so we have a reference. Now when I look at my, my piece of wood, I can see that my 0.6 was pretty good guess, again, assuming that I drew these lines on there correctly. But it's not quite at 0.6. The end there, I'm marking this, the end of it really kind of lines up here, which is just before the 0.6. So if I'm going to make that measurement, I can make a better guess this time. I'm going to guess that between 0.5 and 0.6, this is probably the halfway point. And, it might be halfway between that and the 0.6 mark. So if that halfway point is 0.55, it's somewhere between 0.55 and 0.60. So I'm going to go ahead and say that that measurement is like 0.57. If you disagree with me, and you're welcome to, as long as you say it's somewhere in there, you could say 0.58. That's fine. You could say 0.59 if you really want. But we're getting more accurate. If you notice, the first guess I made was 0.6. The first guess, but I said it could also have been like 0.7. Those are off by 0.1. These two guesses are off, have a margin of plus or minus 0.1. These two guesses have a margin of plus or minus 0.01. So we've gained precision here. We have a more precise answer. We're narrowing how far away we are from the true length of that meter stick because we have more lines on our meter stick. If I put 10 markings on there, look at this. I'm at the 100th or the 100th place, whereas this was at the 10th place. We're actually 10 times more accurate. Go figure. We put 10 times more lines on there than it had before. And not surprisingly, we could do this again. So let's redraw all this here. Let's put 10 more markings. So that 5 was in the middle. 1, 2. I'm not going to be able to draw this. It's too small. 1, 2. Yeah, that's past the range of human. All right, pretend you can see those. That's great. I would need a magnifying glass. I wonder if I can stretch this. Ooh, look at that. Oh, that's red. I didn't mean to do that. Anyway, there you go. So now what we can see, if we draw the dots here, let's try to go all the way down. If I have 10 times more lines on there, it looks like, and again, this is hard to pick out, but I will draw or I will attempt to draw that 0.5 line a little longer. So those lines almost exactly line up with the 0.7, but you might be able to make an argument that it's slightly to the left or slightly to the right. So with this new measurement, I might be able to make something like 0.571. I could say 0.569. If I think it's right on that 0.57, I'm going to say it's 0.570. Okay? Because I can actually measure the 1000th place if I have that many lines on my meter stick. So we're essentially guessing at the last digit. Every time I use this instrument, I'm guessing one final digit there. If I think it's right on there, I'm guessing 0. I think it's right before there, I guess there. But that's my guess. So let's scroll back out here, or zoom back out here. Come on, there you go. So what I'm looking at here is that when there were no lines on the meter stick, it was just one big meter stick. The markings were 0 meters, 1 meters. The markings were at the ones place. They were at this place. But we guess here. We guess at 1 digit further. Because I could guess that it was somewhere, the length of the wood was somewhere between the 0 and the 1. When I had markings that were, every tenth, every 0.1, right? These were definite. Those were marked in the meter stick, so I guessed 1 digit further. And then when I finally did my little markings, again, they were so little they were hard to see, but because the 100th place was marked, I guessed at the 1000th place. And so scientists have come up with a term for all of this about measurements. When you make a measurement, you write down all of the digits that can be measured with the meter stick where there are actual lines for it, and then you write one further guess. And the guess is an uncertain digit, but it tells you the precision of the instrument that you used. This measurement here is definitely not as good a measurement as this one, because it was made with an inferior tool. It was made with a tool that's just harder to read. So you can almost say a bigger number is a more accurate number, and indeed this is a statement that physicists would make. So what we'll say then is that in this number here, all three of these, the 0.5, the 0.07, and the 0.000, all three of those digits are significant. They have been measured by the person who took this measurement, and so we can rely on all three of those digits to a certain degree. This measurement here has only one significant digit. Let me write this. So this has got 3, significant, or significant figures, sometimes they call it, sig figs. And this one over here only has one sig fig, significant figure. And 3 beats 1. 3 is more accurate or precise. 3 gives you more information. The more you can measure with your tool, the better off your calculations are going to be. So we're going to shift gears here. Let's move down a bit. I want to move the whole page down. How do I do? There we go. Okay. New drawing tool, sorry. Let's suppose that you are designing a satellite with a big camera on it. It's going to fly around the Earth, and it's going to take pictures of the Earth. So I'm going to draw the lens of the satellite like it's looking down at Earth. Here's the big photo lens. And somewhere way down below the Earth's very small, so we'll draw the Earth in green. Here's the Earth. It's green. It's got water all over it, okay? And you want to measure things with your satellite. So on the front of the lens, this is us looking down at the Earth. On the front of the lens of the satellite, you put a ruler. Like this. Okay, now if this was really a ruler from a satellite, the distance between those lines would be very, very wide, especially considering how big the Earth is. The Earth is something like 10 to the 6th meters in radius. So let's say that on average, yeah, we could say these are about 10 to the 7th meters, or these are like 1,000 kilometers. So we'll say that between a pair of these lines, that's a distance of 1 million meters. I'm just guessing here, but freehand drawing. But you get the idea. And we're going to measure the distance between, let's say we have some continent. Here's some island right there. And we're going to measure how wide it is. And you, using your sig fig knowledge that you just got, your precision, you say, well, I think that's almost as wide as those two lines are, but not quite. So instead of saying it's 1 million meters wide, we could say it's 900,000 meters wide. And that's as good as you can get with this particular lens. Well, let's be careful with this number. You guessed at that digit. You guessed at the 100,000s place. The instrument can measure to the millions place, so you guess one digit behind that. One digit more precise. Now, the number you write down does have 6 digits in it, but your guess is here. And that's can be misleading. You did not write down a number with 6 significant figures. You wrote down a number with 1 significant figure because the 9 is your guess. And anything past your guess, anything on this side of your guess, does not count. Sometimes you'll see this when you make calculations. You know, you take an irrational number and you divide it in your calculator, and your calculator spits out 3.17815. You know, it keeps going. We're going to find that not all of those numbers are significant, because let's say your calculator guessed at that digit. Everything beyond that digit does not count. Is not significant anyway. If you're guessing here, how could you possibly be accurate about any of these digits behind it? So we'll say that you can only guess one place further. So that's a big number, but it's a big number that only has 1 significant digit. We could do a bigger continent. Let's draw a bigger continent here. There's a bigger continent. Now, this bigger continent actually looks like it goes past 2 widths of line. So this is we'll claim that this continent, according to my telephoto lens, is 2,200,000 meters wide, which is probably impossible. I don't know if we have any continents that are that wide. 2,200 kilometers, maybe we do. maybe that's not unreasonable. So 2,200,000 meters wide. Now, I guessed at this part. I know it's bigger than 2. I know that's a certain digit. But I'm guessing at the 200,000 part. It could be 2,300,000. And again, you're welcome to disagree with me and make your own measurements. So but what I've written down is a number that, even though it's very big, only has 2 significant digits. The certain digit and the guess, the uncertain digit. And everything past the guess, everything past that uncertain digit is not significant to the measurement. I am not that good with my eye. I cannot subdivide. I couldn't say it was like 2,230,000, right? I just can't see into the 10,000s. Not with this instrument. So, this is where the concept of scientific notation comes around. I'm gonna find a new way to write all this. I don't like all of these zeros. So that we don't have to write down these huge numbers with all of these zeros, I'm going to say that I need these 2 numbers. Those were measurements. Those were measured values. I'm going to say that was 2.2. And I'm going to just keep track of all the zeros as powers of 10. 1, 2, 3, 4. This one was 5. And then notice I placed the decimal point here. So I actually have multiplied by another 10. So 2.2 times 10 to the 6th meters. All right, that's my scientific notation. But that also tells me how many sig figs I have. That means that there are 2 significant digits in that measurement. That's what was measured by this. These 10s just tell me how big it is. The measurement is that big. But the only 2 things that were measured were those 2. I could go back to the original measurement where I had like 900,000. That would be 9 times 10 to the 5th meters. And that only has 1 significant digit. So I only write that 1. If it had 2, I mean, if I had measured, if I had put an extra amount of lines on this, I could add more digits to it, but I didn't. Let's do one with a 0 in it, just so you guys can see how that works. So if I draw one more continent, and I'll draw a nice, easy one from here. Oh, that's not even on the Earth. Whatever. There's an asteroid coming to hit the Earth. There you go. And there it is, and we measure it with the lens on my satellite. And I'm going to pretend that when I measure it that it's exactly 3 widths wide, and each of those widths is a million meters. So when I measure that asteroid, I'm going to record that it was 3 million meters wide. But that actually that's a number with 2 significant digits. I can see the 3 markings. Those are marked on my ruler, or in this case on the lens of the telescope. So I'm guessing that it lines right up. I'm guessing 1 digit further, that it's not 3.1 million meters, but it's exactly 3 million meters. But that's still a guess. So my guess is that 0. And then everything past the 0 is not significant. When I write that number in scientific notation, I write it like this. That's the same as 3.0 times 10 to the 6th meters. And that still shows that I have a guessed value, and it's right there. So when you do scientific notation, we're actually keeping track of how well you measured your stuff. And we do it with however many digits show up in the number before the powers of 10. So these powers of 10 do not contribute anything to the significant figures of this measurement. All right? This is still a measurement with only 2 sig figs, which is, again, relatively imprecise. Okay? And you can do this with very tiny measurements. If you wanted to, say, measure the width of a human hair, here's a human hair, and here's your ruler. And those are millimeters. Let's say that your ruler measures in millimeters. Well, the width of that hair is definitely less than a millimeter, and it might even be less than half a millimeter, yeah. So I have to make a guess, and I guess that that hair is 0.2 millimeters. But if that's meters, right, a millimeter is a 1,000th of a meter, so each of those lines is actually 0.001 meters wide, and I guessed that it's not even one of those, it's less than one of those. So I'm guessing that this is 0.0002 meters wide. That's a very, very thin hair. Well, I can, again, zeros. I don't like zeros. That's too many. I want to put the decimal place here. I want it to be right after that first digit. Because I didn't measure these zeros, right? I measured the 2. The zeros just tell me how big it was, just like in the 3 million. I didn't measure all of those zeros after the 3. They just tell me how big it is. So the zeros are only there to mark your place, essentially. They are not measured. So what I'm going to say is that was 2 times, well, these 10s, though, they really weren't, I didn't really multiply by 10 to get this 2. I divided by 10, so we'll make them negative 10s. So that's 2 times 10 to the minus 4 meters. That would get me 0.0002. And again, I don't write anything after that. This was a 1 significant figure measurement. If I had an object that was this long, maybe that's 3.5 millimeters, I would write that is 3.3. Haha. Well, let's say it was 3.3 millimeters, because I can't do halves in my head, obviously. 3.3 times 10 to the minus 3 meters. And that's a figure where I could measure the 3, right? I measured 1, 2, 3 wide, and then I measured there were some extra. So, like that. And that's a 2 sig fig measurement. So again, scientific notation is this wonderful tool that's going to let you look at measurements, immediately know how precise they are in terms of how many sig figs the tool was used to measure them with, and then you use the powers of 10 just to tell everybody how big it was. Now, if you don't like powers of 10, and some people can be confused by them, you shouldn't be. We're gonna practice a lot, so you will eventually get good with powers of 10. We've also come up with prefixes for this. So when we talk about length, we measure things in meters, but when you have little small lengths, like I used a millimeter. I put a little m in front, okay, to signify that they are smaller than normal meters. When you make really big lengths, you have a kilometer, a kilometer, and that K is going to tell you that you're talking about big units of meters. So these all correspond to a certain power of 10. So let's just lay it out, the ones that you're likely to see. And you'll see a pattern here. So let's say that our standard is a meter. That's the base unit. Okay? If you go up by 10, or sorry, if you go up by 1,000 to a kilometer, a kilo of something is going to be a 10 to the third of that something. So 1 kilometer is 10 to the third meters, or 1,000 meters. If you go up even more than that, let's go up to a 10 to the 6th of something. That's 1,000,000 meters. If you go up to 1,000,000 meters, that is a megameter with a capital M. I should probably write these out. Kilo, mega. If you go up to a 10 to the 9th of something, in this case meters, that is a giga. So a gigameter would be 1,000,000,000 meters. And if you could keep going, I think, let's see, kilo, mega, giga, I think tera is 1,000,000,000,000. Exo is with 10 to the 15th or something. They keep going. You will probably in this class use this one a lot, maybe this one a little bit. I don't think you'll get many gigas. But you can go the other way, right? You can make small meters. A millimeter, right? That was the other direction. That's a 10 to the minus 3 of something where you divide by 1,000, so it's 1,000th of a meter. So that's a milli. If you go even smaller than that, so that's a meter stick that's been chopped up 1,000 times, as opposed to 1,000 meter sticks for a kilo. So when you look at a millimeter, it's those little tiny lines on the meter stick. If you were to take one of those tiny lines and chop it up 1,000 more times, you would get something that's 1,000,000 times smaller than a meter, so 10 to the minus 6th of a meter, 1,000th of a millimeter, and that would be a micrometer. So a micro is this symbol here. This is a Greek letter mu that we're going to use for micro. If you chop it up you chop up a micrometer 1,000 times, so we're down to now at 10 to the minus 9th of a meter. You have a nanometer. You've probably heard of that term before. We're going to measure light in nanometers. Or you maybe have done that in chemistry. And if you go down even further, 10 to the minus 12th of something, that's a picometer. And then I always forget the rest. I know there's femto and atto as prefixes, but I don't remember which order they go in. But you can look them up. They're online. So yes, you get very small stuff here. And that way, I mean, using this language can be very quick, right? How big is that thing? Oh, it's 20 nanometers. You just have to be able to do this in your head and say, well, that's actually 10 to the minus 9 meters, or that's 3.56 nanometers. And you would say, that is a 10 to the minus 9, but he just gave me a 3 sig fig number. Good stuff. So those are our units. Let me see if we have anything else we have to hit on. The only other thing that comes up, so you'll do a lot of measurements with meters. We're also going to do a lot of measurements with time. I would say distance and time come up the most in physics. And the same thing works for time. 1.056 seconds, right? That is a number that's been measured with a very accurate stopwatch that counted to the thousandths place. And by the way, most of us now on our phones have digital stopwatches. So they just show the numbers. They don't show like a ruler where you just look see what the second is. That's fine. We always assume that whatever the stopwatch shows, the last number is the guess. And that guess is sort of made by the machine. It's not made by you. That the machine is not accurate enough to be more precise than this last digit. But we can assume that it's not perfect. That the machine was perfect in these categories, but it may or may not be that 6 is correct. That 6 could be 5 or a 7 or something. It read out the 6. So assume that the machine made that guess. The same thing happens with electronic balances when you measure mass. If you have a balance and so here's the plate of the balance, and you put like a rock on there or something, and the balance reads 2.03 kilograms. Okay, that 0.03, that tenths place, that is as sensitive as that balance can read. So that's it. You assume the last place is the guess. And those of you who have taken chemistry probably remember some balances where you put stuff on there, and that last digit was going up and down, and it wasn't settling. It was wavering. Well, that's part of how accurate that instrument was. It couldn't keep that last digit correct. So in that sense, you did have to make a guess for that last digit because that was not as precise an instrument as you want it to be. But hopefully the instrument had these 2 digits correct. So when you record things, that's how you're going to do it. And if we want to just make a connection here, that would be 2.03 kilograms or 2.03 times 10 to the 3rd grams, right? Because a kilo is 1,000 of something. But it's still a 3 sig fig number, because we don't count the powers of 10. Okay, that's your lecture on how to make measurements and properly make measurements with numbers, and how to use scientific notation to write really big numbers or really small numbers, essentially how to turn zeros into powers of 10, and then how to write and what the units are and how their prefixes can be used instead of powers of 10.